Hi everyone, my name is Akhil. My number is 22BQ1A1282. I am from ITB. Today I am here to explain you about the shortest path algorithm. It is also known as the Dijkstra's algorithm. The shortest path algorithm was given by the Dutch scientist in the year 1959. His name is Edgar Dijkstra. It is used to find the shortest distance of a tree. It is also known as the greedy algorithm, which is used to find the shortest distance. It is used in the network system like ISIS and OSPF, etc. Moreover, it is used to find the shortest distance from the source node to the destination node. Now let us consider the example of three vertices A, B, C, D and E, which are having the distance 2, 5, 3, 4, 6 and 8, and it is a directed graph. Now here we need to write these values in the table, which are having, here it is step 0, it is vertex visited, distance from vertex, which means here from A to B the distance is 2, so it is denoted with the dv. The path from vertex, which is denoted with the pv. Here from the B path is from A, B is via A, so it is called pv. Initially the source vertex is A. We need to consider the vertices A, B, C, D, E and visited. Initially all the visiting is 0 and the distances initially are all are infinity except A, and path from vertex is 0. Now in step 1, visit the source vertex, that is A, which are having the non-visited adjacent vertices B and D, and update their corresponding dv values. Here we are visiting A, so we need to consider in place of A1 the distances, the non-visited adjacent vertices of A are B and D, which are having the distance 2 and 4. For A is visiting B, which is having the distance 2 via A, and A is also visiting B, which is having the distance 4 via A. In step 2, we need to find the non-visited adjacent vertices of whose dv is minimum. Among B and D, here the minimum dv is 2. So here in B we need to consider the non-visited adjacent vertices. Here the non-visited adjacent vertices of B are E and C. Now we need to update these dv values. Here the non-visited adjacent vertices of B is C. C. The distance from B to C is 5. We doesn't consider that B to C directly. We are checking from path A to B and B to C. And the total we need to consider 2 plus 5, that is 7. 7. It is via B. And also B is also visiting the vertex E. We need to consider the distance from A to B and B to E, that is 2 plus 8, 10. The distance from E is 10 via B. So the path from A is completed. Again we need to consider the non-visited adjacent vertices whose dv is minimum. Here among C, D, E is remaining not vertices not joined, so the minimum dv among these three is 4, so we need to consider the d, that is 4. From the distance A to D is 4 minimum distance, so we need to leave it as same, but we need to consider the visited as 1, and also the path from A to D is completed, and it is also known as the shortest path. Here we need to consider the shortest path from A to D is 4. If here A, B, D is completed, there are remaining 2, C and D. The shortest distance from both the whose minimum dv is 7, which is having the vertex C. So we need to consider the vertex C. which is having the small distance. So we need to keep here 1. And the shortest distance is 7. Remaining 7 via B. So the distance from A to B and B to C is B to C is 5, but we need to consider the full path from A to C. So 2 plus 5 is 7. We need to remain it same. Again, if you take A is completed, B, C and D is completed, the remaining E, which is having the distance 10. And here there is only one way of path distance, that is A to B and B to E. It is the shortest distance, so we should calculate and we should remain it same as, but here we need to consider it as 1. From A to E is 8. It is the shortest path distance. All the vertex are visited and the dv is calculated and path also is calculated. So the final graph is A to B is distance 2, A to C is distance 7 via B, A to D is distance 4 via N, A to E the distance is 10 via B. Thank you.